Hello everyone. Today we continue with the discussion, the paper discussion of yesterday's paper. Okay. Yesterday's question paper discussion we are going with. Yeah. So the first question is what here? The first one is which of the following expressions, correctly represents the van der Waals equation of state? So we know van der Waals equation. This van der Waals equation is for which one? For which gases? For real gases. Real gases means what? Non-perfect gases. Non-perfect gases or non-ideal gases. For these gases, we give what now here? This one has what here? Answer. So here pressure of real gas plus pressure correction. Plus pressure of real gas plus what? Some pressure correction. A square by V square into volume of real gas minus volume correction. Volume of real gas minus volume correction. Okay, is equal to N into RT, nRT. N is number of moles here. So it is what now here? Real gas equation. So for real gas equation, the van der Waals has given one equation called van der Waals equation of state for real gases. In this, he has introduced what? Pressure correction and volume correction. He added pressure correction to real gas pressure and he has subtracted the volume correction from real gas volume. Next, the temperature at which a real gas obeys, means real gas follows the ideal gas laws over a wide range of pressure is called what? So the temperature at which real gases are behaving like what? Real gases obey what? Ideal gas behavior. Okay, this is what now the temperature is what? Boyle's temperature. So the Boyle's temperature is what? The temperature of a gas at which it behaves, the temperature of a real gas at which it behaves like what? Ideal gas is called Boyle's temperature. And what is critical temperature? The temperature below which the temperature of a gas, the temperature of a real gas, below which only it can be liquefied. The temperature of a real gas below which only the real gas can be liquefied is called what? Critical temperature. And what is inversion temperature? I told you inversion temperature is what? The temperature of a real gas, the temperature of a real gas below which if it is compressed, it will exhibit cooling effect. Okay, the inversion temperature of a real gas is the temperature below which if the real gas is expanded, the real gas is expanded, it will show what? Cooling effect. And above this inversion temperature, if the gas is expanded, if the real gas is expanded above this inversion temperature, we get what now? Here? Heating effect. So heating effect and cooling effect, two types of effects will be shown by this gas. Yeah, sorry, ma. See, listen here. So the temperature at which real gas obeys ideal gas is Boyle's temperature. Okay. So here, in this case, inversion temperature. Inversion temperature means the temperature of a real gas below which, if the gas is expanded, it will exhibit which effect? Cooling effect. But above this inversion temperature, when the real gas is expanded, it will show heating effect. That is called inversion temperature. We are going to discuss about this. Next, reduced temperature. So these are not necessary here. So these three temperatures will be there for real gas: critical, Boyle's, and inversion temperature. Okay. So these points keep in mind here. So it's about what now here? It's about what? The different types of temperatures of real gases. So answer is Boyle's temperature here. Next, a real gas expands. A real gas is expected. A real gas is expected to exhibit maximum deviations from ideal gas behavior at what? So generally we know that at very low pressure and high temperature, real gases behave like what? Ideal gases. Where real gases will behave like ideal gases? At very low pressure and high temperature. At very low pressure and high temperature, what happens? Real gases behave like what? Ideal gases. Ideal gas. Why? At very low pressure and high temperature, the deviations will be minimum. The deviations will be minimum and neglected. That's why the real gas behaves like what now here? Ideal gas. At very low pressure and high temperature. Now reverse of these conditions what? Reverse of these conditions what? High pressure and low temperature. At high pressure and low temperature, if you take reverse of these conditions, if you take, in that condition, what happens now? Real gases will deviate to the maximum extent. Real gases will deviate to maximum extent. So here, what is asked here? A real gas, okay, is expected to exhibit. A real gas is expected to exhibit what? Maximum deviations from ideal gas laws at low temperature and high pressure. At these conditions, more deviations will be there here. More deviations will be there here. If you take high temperature and low pressure here, if you take high temperature, low pressure, real gas behaves like what? Ideal gas. Real gas behaves like ideal, because here minimum deviations. That's why the real gas behaves like what now here? Ideal gas in this condition. But here what now here at low pressure and high temperature, maximum deviations. So here what is asked? Maximum deviations they asked. That's why answer is what this one, 43, first option. Next, in Maxwell velocity distribution, in Maxwell's distribution of molecular velocities, the curve, the peak of the curve point, okay, corresponds to what? If you take what now here, fraction of molecules, and if you take what now speed, the molecular speed, the fraction of molecules versus molecular speed, if you take, we get what one curve, this one. So this type of curve we get here. So this peak of the curve represents what now here? Which velocity? It is most probable velocity, UMP. UMP means what here? Most probable velocity. This most probable velocity indicates what? This peak of this curve. And this indicates what? The number of fraction of molecules. The fraction of molecules possessing this most probable velocity. So this indicates what now here? Most probable velocity. Is that clear? So answer is most probable velocity, UMP. So what is the most probable velocity definition? The velocity possessed by the maximum number of gas molecules. The maximum number of gas molecules will possess most probable velocity, remember. Okay. Next one. Among the three types of velocities, UMP, U average and U RMS. If you take three velocities among these, which has greater value at a given temperature. Greater value means what now here? Greater magnitude. Value meaning what here? Magnitude. So magnitude is greater for what? Magnitude is greater for RMS velocity. So RMS velocity greater than what? U average. U average magnitude is greater than what? UMP. Now, whose magnitude is the least? Most probable velocity of a gas is least. But whose magnitude, whose value is greater? RMS velocity magnitude is greater. But which velocity is possessed by maximum number of gas molecules? Most probable velocity. This most probable velocity will be possessed by maximum number of molecules in a given gas. So that point mainly we have to understand. Okay, ma. So it's about what now here? The conditions of what? The order of what velocities. Is that clear? Next one. At the same temperature, which of the following pair of gases? Which of the following pair of gases will have the same RMS velocity? Same RMS velocity should be there when temperature is same. That means what now here? The T1 temperature, the T1 of first gas is equal to T2 of second gas. Temperature of first gas and temperature of second gas same here. Which of the following pair of gases? Which of the following pair of gases will have same RMS velocity they're asking here. Now if you take RMS velocity formula, U RMS velocity is equal to under root 3 RT by M, right? 3 RT by M. If you take for the first gas, it will be 3 RT1 by M1. 3 RT1 by M1. And if you take second gas, 3 are T2 by M2. T2 of second gas, M2 of second gas, molecular mass of second gas. Now, how molecular mass and velocity related here inversely now? So RMS velocity is inversely proportional to square root of molecular mass. And temperatures are same, they said. Temperatures are same. Now temperature is constant, R value constant. 3RT will be constant. Then what will be variable for two gases? Gram molecular weight will be changing. Okay. So when these two gases have same RMS velocity means what? Anyhow, the 3RT value same for two gases, because temperature of first gas is equal to temperature of second gas. So 3RT value will be same for both gases. If molecular mass also is same, if molecular mass of two gases also is same, RMS velocity of first gas will become equal to RMS velocity of second gas. So what we have to check now here? Gram molecular masses we have to check. It is propane. 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 So here C3 means what? 12 3s are 36 plus. Here how many hydrogens? 8. So 36 plus 8, how much? 44. 44 grams per mole is gram molecular weight of propane. And CO2 gram molecular weight we know. C 12 plus 32. So 44 grams per mole. Okay. So what is the gram molecular weight here? 44 and 44. These two gases, propane and CO2 carbon dioxide, these two gases have same molecular masses. When they have same molecular masses at the same temperature, they will have what? Same RMS velocity. But remaining cases here, gram molecular mass is 71 grams per mole. Here 32. Here oxygen 32. Ozone 48. And CO2 44 here. And here CO 28 gram per mole. Like this, only in this option, the same molecular mass is there for two gases. Next, which of the following gas molecules have the greatest average molecular speed at given temperature? Now, temperature is what now here? 100 plus 273. Kelvin temperature only we have to take. Okay, that is what now here? 373 Kelvin. So 373 Kelvin is temperature given. And what they ask here, which of the following gas molecules have greatest average velocity? Greatest average velocity, that's there. So what is the formula of average velocity? Average velocity formula is given by what now? So most probable velocity 2RT by M, under root 2RT by M. RMS velocity under root 3RT by M. And average velocity what? Under root 8RT by what? Pi M. 8RT by pi M. Now what they're asking here, which of the following gas molecules have the greatest average molecular speed at given temperature? Now same temperature for all gases. Okay, same temperature for all gases. Same temperature for 4 gases given here. For 4 gases mentioned in the problem. In options, how many gases given? 4, na? For 4 gases, same temperature we have to take. So temperature remains what now here? Constant for given all 4 options. In case of 4 gases, temperature is same, R value same, pi value same. So 8RT by pi, 8RT by pi will be same for all gases. Then we have to consider what? Gram molecular mass we have to consider. Now how average velocity and gram molecular weight related here? So average velocity is inversely proportional to square root of what? Gram molecular weight. Okay. Now if gram molecular weight is less, average velocity will be maximum. So they're asking greatest na here, greatest average velocity. That means the molecular mass should be least. So here carbon dioxide na 44 gram per mole. Chlorine what? 71 gram per mole. Nitrogen for here Cl2 71. For nitrogen N2 gas it is 14 plus 14 na 28 grams per mole. Okay. And oxygen what? 32. Okay, like this what now here? Least molecular mass is there here. So when molecular mass is least, average velocity will be highest, greatest. Is that clear, ma? So molecular masses we have to check. Next, the gases contain 10 power 22 molecules and 10 power 23 molecules present in different vessels. So volumes are different, different number of molecules. Different number of molecules there and in different vessels with different volumes. At the same temperature, they're saying. Temperature is same for 2 gases. Temperature is same but different volumes are there, different molecules are there, number of molecules. The ratio of their average kinetic energy. Average kinetic energy means per molecule. Kinetic energy per molecule is called average kinetic energy. Okay, so kinetic energy per molecule is called what, ma'am? Kinetic energy per molecule is called average kinetic energy. So average kinetic energy average is given by what now here? 3 by 2 kT. 3 by 2 kT. K is what now? Boltzmann constant. Boltzmann constant is what? Universal gas constant by Avogadro number. Universal gas constant by Avogadro number, R by Na, is called what? K, Boltzmann constant. So this is average kinetic energy per a single molecule of gas. So average kinetic energy is directly proportional to what? Temperature, na? Kinetic energy and temperature, how they are related directly. Okay, so here what they are saying, same temperature they are saying for two gases. When temperature of two gases is same, they will be having same kinetic energy. Because in the formula of average kinetic energy, any gram molecular mass mentioned here, gram molecular mass is not there. K is Boltzmann constant, same for all gases. And next one, T value. T is what now here? Temperature. Now temperature also is same for two gases, they said. When temperature is same, kinetic energy average will be same. That means what now here? The average kinetic energy depends only on what? Temperature. It does not depend on the nature of molecule, number of gas molecules, and volume of gas molecules. But only the kinetic energy depends on what your temperature. That's why the same ratio will be there. Kinetic energy of two gases must be same because they are taken at same temperature. So kinetic energy is only dependent on temperature. Is that clear, ma'am? Next, the temperature at which RMS velocity of CO2. The temperature at which RMS velocity of CO2 is equal to RMS velocity of N2O at 27 degrees Celsius. A CO2 gram molecular weight is how much? Gram molecular weight of CO2, 44. Right, ma'am? And here N2O means nitrous oxide, laughing gas. Laughing gas, nitrous oxide formula what, ma'am? N2O. That is nitrous oxide. Here N2 means 28 plus 32. Sorry, 16. For oxygen, how much here? 16. So how much it is now here? It is what now here? 14. Okay. And it is 44. Okay. So what is now here? So 14, 2, 3, 4. So 44 grams per mole here. So CO2 44, N2 also 44. Gram molecular mass is same. Gram molecular mass is same for two gases. What they're asking now, the temperature at which RMS velocity of CO2 with gram molecular mass 44 is equal to the RMS velocity of N2O with gram molecular mass 44 at given temperature. Now, what is the formula of RMS velocity? RMS velocity is given by under root 3 RT by M. 3 RT by M. So URMS is equal to what? Under root 3 RT by M. So in this case, what they are saying now here, molecular mass is same. 3R value will be same. 3R will be same for two gases, and molecular masses of CO2 and N2 also same. Now in this case, temperature we have to consider. Now they are saying what now? At given temperature of N2O, sorry, whatever the temperature of N2O, and the same temperature CO2 must be used here. Because molecular masses same now here. Molecular masses are same. That's why here, if N2O is taken at 27 degrees Celsius, that is 300 Kelvin, then CO2 also must be at same temperature. Then molecular masses will be same, temperatures will be same for CO2 and N2O. When molecular mass and temperature both are same for two gases, they will have same RMS velocity. That's why here N2O is taken at 27 degrees Celsius and CO2 also should be taken at 27 degrees Celsius because these two gases have what? Same molecular mass. Same molecular mass. That point we have to understand. Next, 50th one. 50th one at 27 degrees Celsius. At 27 degrees Celsius, the ratio of RMS velocity. The ratio of RMS velocity of ozone to oxygen. Now ozone gram molecular mass is what now here? Ozone O3 na? O3. So what is the gram molecular mass here? So M1 is equal to what now here? 48. 48 gram per mole. Next, O2, oxygen. For oxygen, what is the molecular formula here? O2. So M2, molecular mass of second gas is what now here? 32 gram per mole. 32 gram per mole. Next one here, they asked what now here at given temperature. At the given temperature, both gases have same temperature now. Molecular masses are different. The ratio of RMS velocity of ozone to RMS velocity of oxygen. So what we have taken now here, RMS velocity of ozone first. So here it is what now 3 or T. T is same for both gases. By what now here? Ozone, molecular mass of ozone, how much? 48. Divided by 3 RT. 3 RT by oxygen molecular mass, how much more? 32. So the ratio you take here. This ratio will be what now here? Square root of 2 by 3. Under root 2 by 3 will be the answer. Okay, ma'am. So here T value same, R value same for both gases. But only molecular masses will be changing, 48 and 32. So this ratio they asked. Next, the expression, the compression factor of a gas is more than unity. The compression factor means compressibility factor. So compressibility factor Z, okay, compressibility factor Z is greater than 1, they say. So Z is greater than 1 means which deviation? Positive deviation. Positive deviation of gas. The real gas is showing what? Positive deviation. Positive deviation. When Z value is greater than 1, unity means 1 only here. Okay. So when Z value greater than 1 at STP, its molar volume. Vm stands for what now here? Molar volume. Molar volume meaning what? The volume of 1 mole of gas. Volume of 1 mole of gas is called molar volume. Generally, molar volume how much? 22.4 liters now at STP. Here, when Z value is greater than 1, molar volume should be greater than 22.4 liters, I told you. When Z value is greater than 1, molar volume should be greater than 22.4 liters. That's why the molar volume should be greater than 22.4 liters. So it is what now here, given what now, molar volume should be greater than what? 22.4 liters. 1 liter is equal to 1 decimeter cube, I told now. 1 decimeter cube, 1 liter, both same. That's why 22.4 liters. Greater than this value should be there. If Z value is less than 1, suppose, if Z value is less than 1, this condition we take. If Z is less than 1, Z is less than 1 means negative deviation. In that condition, molar volume will be less than 22.4 liters. But here they gave more than unity, greater than 1. So the answer should be this one. Next, the density of a gas molecule is equal to, formula what now? D is equal to, density is equal to Pm by Rg. Na? Density is equal to Pm by Rg. Okay, so we have derived this one from what? PV is equal to Nrg. From this we have derived. N is equal to mass by molecular mass. These all things we have taken. So from this we can derive what? Density is equal to Pm by Rg. Next, 3.5 grams of carbon monoxide. Carbon monoxide. What is the gram molecular mass? 28. 28 gram per mole. 28 grams per mole. And given weight, how much here? Given weight is what? 3.5 grams. So mass is given 3.5 grams. Molecular mass is what now? 28. What is the number of moles? Formula for number of moles. Weight by gram molecular weight. And what is the temperature given here? This one. So 0 degrees Celsius means 273 Kelvin, and 760 mm pressure means 1 atm. They give 760 mm is equal to 1 atm, na? And 0 degrees Celsius equals to 273 Kelvin. Now these conditions what? STP conditions only, na? STP they give here. So it STP means 273 Kelvin, otherwise 0 degrees Celsius. 760 mm means 1 atm. Okay. So at STP conditions or NTP, STP or NTP you take here. STP or NTP. So at STP or NTP conditions, okay, it contains how many molecules? Generally, we know that gram molecular mass, gram molecular weight, that is 1 mole. Yeah, 28 grams here, 28 grams per mole. So that is for 1 mole. So 1 mole CO2, 1 mole CO, 1 mole CO. So 1 mole CO contains what now here? 1 mole CO contains how many molecules? 6 into 10 power 23. 6.023 10 power 23 molecules. Then at STP, Here, how many moles given? 3.5 grams by how much? 28. So these many grams, these many moles. So one mole CO, 1 mole CO is occupying, having what now? 6.023 into 10 power 23. So these many moles will contain how many moles? That's what they ask. Is that clear, no? So we have to take what now here? 7.5 into 10 power 22 molecules. Is that clear? So do the calculation parts. Next, the average speed at T1 Kelvin at given temperature T1 and most probable speed at T2 Kelvin of CO2 gas is given here. Is that clear, ma? Now the values of T1 and T2 are what? The values of T1 and T2 are what? Now here what is to be observed here? It is given in centimeters per second, right? CGS they mentioned, CGS units. So if you want to convert into MKS unit, MKS in meter per second, na? So 1 centimeter, how many meters, ma? 10 power. 1 centimeter is equal to 10 power minus 2 meters. That's why we write what now here? 9 into 10 power 4 into 10 power minus 2 meters per second. So in place of 1 centimeter, we have taken what? This one. So 1 centimeter is equal to 10 power minus 2 meters. That's why here 9 into 10 power 4 given into, in place of centimeter, we have written 10 power minus 2 meters per second. So it is about 9 into 10 power 2 meter per second. In MKS, we have taken in MKS system. Okay. Now what they said, you see here. So this 9 into 10 power 2 meter per second. Okay, is equal to what now here? Average speed. Average speed formula what now here? Under root 8 R T. T is what now here? T1 now for this T1 RT, 8 RT by pi. Okay, M. So here what they said here, which gas? CO2, same gas now for both cases. In both cases, T1 terms, both will be given, both are given what? CO2 only. CO2 means it is constant here. It is constant, 8R by pi constant. 8R by pi M will be constant. Is that clear, ma? So it is equation 1. Now equation 2 is given what? 9 into 10 power 2 meter per second. The same thing will be equal to what now here? What is given here? Most probable speed. Most probable speed formula what? 2 RT. T means here T2. Right, ma? T2 here. T2 given by 2 RT under root 2 RT by M. M is what now here? Same. CO2. Now here it will be constant. 2R by M will be constant here. In this case, 8R by pi M will be constant. 8R by pi M will be constant. Here T2 temperature. That will be equation 2. So on solving T1 and T2, we can calculate. Okay. So equation 1 by equation 2, we can take and we can do it what now here? Calculation part. So we get 1684 Kelvin, 2143 Kelvin. Please go through this and please do this calculation part on your own. Take screenshot and do calculation part. Okay. Please take the screenshot now. Is it over? Yeah, next. The kinetic energy of n molecules of hydrogen is given 3 joules. 3 joules given. Kinetic energy of n number of molecules of hydrogen given what? 3 joules. At what temperature? T1 temperature. T1 temperature is how much given here? Minus 73 plus 273. It is 200 Kelvin. Right, ma? 200 Kelvin given. The kinetic energy of the same sample of hydrogen at 127 degrees Celsius. Means what is T2 given here? What is T2 given? What here? 273. 273 by what? Sorry, 127 plus 273. So 170, 127. Just a minute. Yeah. So 127 plus 273. Okay. So it is what now here? 400 Kelvin. So it is 400 Kelvin T2. T2 is 400 Kelvin and T1 is what? 200 Kelvin. Okay. And now here, what they asked to find out here, the kinetic energy of n molecules of hydrogen is 3 joules at given temperature T1. And the kinetic energy of the same sample of what here H2 at what at another temperature. So here Ke1 by Ke2 is equal to what you take now here, N1T1 by N2T2. Okay, so N1T1 by N2T2. Do this calculation part. Okay, so the ratio, the means what K, this one Ke1, how much here now here? 3 joules. Ke2 we have to get. Okay, so anyhow the same sample means same number of moles to take, same number of moles. Then what will be temperature here in this case now? Temperature initially given what now here? 200, and T2 temperature what? 400. Okay, so it is what now here? 3 by Ke2. 3 by Ke2 is equal to what now here? 1 by 2. Then Ke2 is equal to what now here? 6 joules. Okay, ma'am. So this way 6 joules we get here. Next, compressibility factor for hydrogen behaving as real gas is what? Now for hydrogen and helium, always Z value will be greater than 1, always positive deviation. So hydrogen gas and helium gas, these two gases will always show what? Z value greater than 1. So hydrogen and helium, these two gases always show what? Positive deviation, Z value greater than 1. That means what now? Compressibility factor should be 1 plus something. So Z value is equal to what? 1 plus some value here. So greater than 1 it will be. Greater than 1. Okay. Next. The density of a gas at 27 degrees Celsius and 1 atm is this one here. So at T1 temperature, P1 pressure, D1 is given here. Now pressure remaining constant. That means P1 is equal to P2. The temperature at which the density becomes what? 0.75. D2 is given here. So here it is, the density D1 is equal to what now here? 1D. Okay, here D2 became 0.75. Here 1D, here 0.75D. So we have to calculate this one. Okay, so the relation already we have discussed. Okay, so that relation we have to take it. Density formula, what tell me? D1 is equal to Pm by RT. And here P is constant for both gases. R value constant. Right, ma'am? And also what now here? The same gas they mentioned here. Both cases same gas here. Now here it is what temperature is changing. For first gas it will be T1 temperature and D1 will be density. Okay, so the density of a gas is given, the pressure remaining constant, the temperature at which density becomes what? So molecular mass will be same, pressure is same, R value is same for both gases. So D and T will be changing. Next, 4 molecules of a gas have velocities V1, V2, V3 and V4. Four velocities given here. Okay, the RMS velocity of molecule. So how to find RMS velocity, and what is from definition? What is this here? RMS velocity is under root V1 square plus V2 square plus V3 square plus V4 square by what now here? N number of molecules. How many molecules we have taken? 4 molecules we have taken. So V1 square plus V2 square plus V3 square plus V4 square by 4 we have taken. 4 molecules I mentioned here. So what here now? Square of RMS means what? Root of, mean of, average of, square of velocities. RMS velocity. From the formula we have to take it. Okay. Please write down and do it later. Take screenshot. Have you taken? Next. The pressure of a real gas. The pressure of a real gas is less than the pressure of ideal gas. Generally, pressure of real gas will be what now here? Less than the pressure of ideal gas. Why? In ideal gas, the molecular interactions will be negligible. Okay, and here increase in intermolecular forces. Where in increase in intermolecular forces in real gases. In real gases, the intermolecular forces will be more. That's why the pressure becomes what? Less. Therefore, pressure of real gas becomes. Therefore, pressure of real gas becomes less. Becomes what? Less than ideal gas. The pressure of real gas becomes less than ideal gas. because in real gas, what happens? There will be increased intermolecular attractions. But in ideal gas, there are no intermolecular attractions. Okay. Next, 5 moles of O2. 5 moles, N is given 5 here, number of moles. And O2 means molecular weight, how much? 32 grams. And diffused through a porous partition in 30 seconds. In T1, in 30 seconds time, what happened here? The gas is diffusing here. How many moles of hydrogen can diffuse through the partition? Okay, through the hole in 60 seconds. The T2 is given. T2 is given, T1 is given. Okay, under the same conditions. Here, what is M1 is what? 32. M2 is what for hydrogen? M2 is 2. M2 is what? Gram molecular weight 2. And under same conditions of pressure and temperature, they ask here. Okay, how many moles? N2 they ask here. N2 of hydrogen they ask, N1 is given here. So what is the formula here? R1 by R2 equals to under root M2 by M1. Okay, R1 is equal to what now? Number of moles of first gas by time of first gas. So this one we had to substitute. R2 is equal to